This research proposes a hierarchical navigation module capable of high-speed legged locomotion even in complex and discrete terrain distribution environments, and performing extreme parkour maneuvers such as running on walls or jumping over large gaps. The proposed navigation module robustly operates in complex environments composed of various types of obstacles. We have structured the entire pipeline into 3 modules: the planner module, the tracker module, and the target updater. The planner module generates a feasible foothold from the map. The target updater changes the target foothold for the robot to step on. The tracker module controls the robot to accurately step on the given target foothold. We first trained the tracker module to achieve high performance during the training stage. The tracker module was trained using reinforcement learning on the RASM simulator. We employed a generative model called Map Generator, which evolves adversarially with the tracker module to provide desired difficulty environments. At deployment stage, we can observe the operation of each module on the real experiment. While the tracker module is operating, if the robot sufficiently steps on the target foothold, Target Updater updates the foothold target. When the front target is updated, it activates the planner module. The planner module runs simultaneously on a detached thread. While the tracker module controls the robot to precisely step on next target, planner module generates a feasible and safe foothold plan. To reduce time complexity in planning, the rear foot steps where the front foot has stepped. Planner draws multiple foothold samples through random sampling and rejects risky and difficult footholds using a consecutive filtering structures. Subsequently, the candidate foothold plans are evaluated through rollout in the physics simulation, and the one with the lowest cost is selected and provided to tracker as a next target. The planning module performs sampling and rollouts in parallel across 8 different threads, separate from the tracker module. The real robot controlled by the tracker module is depicted in gray, while the rollout process is shown in blue. The final goal position is represented by a light green cube. The robust navigation module performs well even on maps with various unstructured obstacles. These maps include maps with pillars of various shapes and heights arranged sequentially, maps with impassable pillars or pits in discrete terrains, maps with 1.1 meter patches tilted randomly up to 30 degrees, maps with steps of varying heights and lengths, maps with consecutive ramp pillars of various heights and angles, and maps requiring descent or ascent of high ledges. The navigation module operates robustly even when the goal position is suddenly changed. It can traverse approximately 90 meters through maps with mixed obstacles at an average speed of 2.7 meter per second and maximum speed of 3.63 meter per second without a single failure. This experiment demonstrates the powerful performance of the tracker module. A map requiring ascent and descent of 0.6 meter obstacle. A map requiring side flutter. A map requiring jump across gap up to 1.3 meters wide. A map requiring traversal of double ramps facing in opposite directions. A map consisting of triple consecutive ramps. A map requiring running on a single wall. The following video demonstrates the performance of the entire pipeline in a complex environment. The scenario involves a map with stairs and various obstacles, where the goal is positioned on the right. As before, the scenario involves a map with stairs and various obstacles, but this time the goal is positioned on the left. This scenario involves a map with various sized boxes and ramps, where the cost for avoiding height changes is low. This scenario involves a map with various sized boxes and ramps, where the cost for avoiding height changes is high. This scenario involves a map with boxes and slanted surfaces requiring abrupt directional changes with gaps up to 1.3 meters wide.